Alright, so in the previous video, we have learned that a sample space is a set of possible outcomes of a random experiment, and an event is defined as a subset of the sample space. We say that if any of the outcomes is observed as the result of the experiment in that event E, then we say that event E occurs. So because the events are defined as subsets of the sample space, every type of set operations are also valid operations for events as well. So as you can define the union of two sets, we can also define the union of two events as well. So what is a union event? Let us assume that we have defined two events, E and F, in the same sample space S, and we define the union event as E union F to consist of all outcomes that are either in E or in F or in both E and F. So all outcomes that are contained in both sets, they form the union event, which is another event. Now, consider the experiment where we flip two coins consecutively. Because we are flipping two coins, each coin flip has two possible outcomes, and as a combined experiment, two coin flips would have four possible outcomes by the basic principle of counting, which are double head, double tail, first tail, then tail, head, then tail, or first tail, then head. So the sample space contains these four possible outcomes. Now we define an event E, which is getting the first flip head. Now, if you observe the outcome of this combined experiment, a head-head or head-tail, you can say that the first flip is a head. So these two outcomes, they form the event E as a subset of the sample space. Event F is defined as the event of getting different results in two flips. Therefore, the outcomes head-tail and tail-head, they form the subset representing event F. Now let us define the union event of these two events, E union F. So all outcomes contained in either E or F or both of them are going to be listed in the union event. So head-head, head-tail, and tail-head here are going to be a part of the union event. Now, how can you define qualitatively the union event? That is, getting at least one head. Okay, so getting the first flip head or getting different results in two flips, the union of these two events is defined as getting at least one head as a result of this experiment. Now, when the union event occurs, this means at least one of these two events, E and F, has occurred. Okay, so therefore we say that E or F occurs. So this union stands for or. If union occurs, then we say E or F occurs. If E or F occurs, then the union occurs. If you remember the Venn representation of the sets, we can draw a rectangle or a Venn representation of the sample space here. And the events E and F are going to be subsets of the sample space. And the shaded region, which contains all outcomes that are either in E or F or in both of them, is giving us the union E union F. Now, just like the union operation, we can perform an intersection operation on the events which are defined in the same sample space. Again, imagine you have two events, E and F, defined in the same sample space S, and now we define a new event, E intersection F. E intersection F consists of all outcomes that are both in E and in F. So the common outcomes of E and F, they form the intersection event. Again, we are going to provide an example on the same random experiment, two consecutive coin flips, which has the sample space here. Now, let us define event E. Event E is defined as getting the second flip tail. The second flip is a tail if you observe the outcome head-tail or tail-tail. Therefore, TT and HT, they are the outcomes that should be in the subset E. And event F is getting the same result in two flips, which means event F contains the outcomes head-head and tail-tail. And let us define the intersection event, E intersection F, which is the TT only. So there is only a single common element in both sets, which is tail-tail outcome only. So in this example, the intersection set consists of only a single outcome. And how can we give a qualitative definition for the intersection event? It is basically getting two tails as an event. So the intersection event of E and F is defined as getting two tails. If I tell you, as a result of this experiment, the second flip is a tail, and we have got the same result in two flips, and you would automatically understand, right, that we have two tails. So if the intersection F occurs, we say both E and F occur. Or if both E and F occurs, then the intersection occurs. Okay, so you see, unlikely to the union event, in between two events, we write an and if we are talking about the intersection. So if the intersection event occurs, imagine the outcome is TT, tail-tail, then you can also say that event E and event F, they both occurred, right? Because tail-tail is contained in two of the sets as well. Or if you observe that there is an outcome as a result of this experiment, which are contained in both events, in that case, you would say that the intersection event occurs. Now, again, in the Venn representation, the intersection event of two events defined in the same sample space is represented by this shaded region, which contains the common outcomes of event E and event F. Now, of course, not every two events defined on the same sample space have a non-empty intersection. So sometimes the intersection of the events can be empty. They may not have any common elements. So imagine these two events, E and F, of a sample space S. We say that they are mutually exclusive, or we say that they are disjoint if and only if the intersection of these events is empty. So if and only if, this means that this is a definition, okay? So the definition of mutually exclusiveness for two events is a fact that their intersection is an empty intersection. So in the same sample space, if you define two events, E and F, the intersection of which is empty, and you say they are mutually exclusive, or they are disjoint. They do not have any common elements. And mutually exclusiveness means they cannot occur at the same time. They are mutually exclusive. Either one of them can occur or none of them can occur, but both of them cannot occur because these are mutually exclusive. Now, imagine the same experiment again where we flip two consecutive coins and we define event E, getting the same result in two flips. Now, the outcomes of tail-tail and head-head correspond to this event. Therefore, this event is represented by subset E. And if we define event F as getting different results in two flips, the head-tail and tail-head outcomes will correspond to event F as a subset again. Now, you see E and F here, they do not have any common elements. Their intersection is empty. Therefore, we say that they are mutually exclusive, which means they cannot occur at the same time. Now, again, with Venn representation, we can show mutually exclusive events in this form. Imagine we have a sample space here in the rectangle form, and we have defined two events, E and F here. Because they do not contain any common elements, we say that they are disjoint or they are mutually exclusive. So therefore, they cannot occur at the same time. Now, another concept that we can define in set theory is the complement set, as well as we can define it for the events as well. What is a complement event? Now, imagine a sample space S and a subset or an event defined in that sample space E. Okay, we define EC or E complement. So C here, written as a superscript over E, stands for complement, the word complement. So this C here is the first letter of complement. So E superscript C is basically the complement event of event E, and that set, the complement event, consists of all outcomes in the sample space which are not in E. So E as a subset, as an event, contains some of the outcomes in the sample space, and E complement contains everything else. So imagine two consecutive coin flips experiment again, and you have this sample space once again. And if you define event E as getting tails in both flips, then event E will simply be what? It is just going to be TT, tail, a single outcome. Okay, so event E here is a single element subset. Now, E complement, the event E complement, of course, it is also another event because it is also a subset, is going to contain anything else. Anything else that are not contained in E. Okay, every other outcome in the sample space which are not contained in E is going to give us E complement, and E complement means getting at least one hex. As you can see, if you have any other outcome, in any other outcome, we observe at least one hex. Now, please notice that if you take the union of an event and its complement, so E union E complement will give you the whole sample space. Okay? And that means if you perform this experiment, either E or E complement will occur because everything, all outcomes are either contained in E or E complement. Okay? So what does that mean also? Either E will occur or E will not occur. So the fact that E complement occurs means E does not occur. So for any event, when you perform an experiment, for any event, one fact we are going to say definitely is that event may occur or may not occur. Okay, there are two situations here, and therefore we can say that either E or its complement will occur. As another fact, we should state that because the complement event contains everything else except the ones in E, their intersection would be an empty set. Because of that reason, we should say that an event and its complement are mutually exclusive, which means they cannot occur at the same time. You cannot say an event has occurred and at the same time it has not occurred. Okay, it is impossible. Therefore, we say that complement events are mutually exclusive, which means they cannot occur at the same time. However, because their union gives us the whole sample space, one of them must definitely occur. Now, again, in the Venn representation, we have this sample space in the rectangle form and a subset or event E defined in the sample space. The shaded region contains all outcomes which are not in E. Therefore, we say that the shaded region gives us the complement event. Now, at this point, we are going to talk about the De Morgan laws. Okay? There are two laws of Augustus De Morgan, who has lived in the 19th century. These two laws are very practical formulations that we can utilize in probability calculations, which we are going to see basically as a part of this chapter. Now, these laws are basically defined in the set theory, but because events are defined in the form of sets, they can also be utilized in probability theory as well. So what is the first law of De Morgan? The first law of De Morgan says that the complement of the union of two sets is the same as the intersection of the individual complements. So if you check left-hand side, the complement of E union F in the Venn representation is the shaded region. So this shaded region here is the complement of E union F, because anything else outside the union of these two events gives us the complement. Now, if you check the right-hand side, we are looking for an intersection. An intersection means the common part of two events. However, the events we are talking here are the complement events. So where is E complement? Okay, the E complement is anything else outside event E. Anything else outside event E. And F complement is anything else outside event F. Now, the intersection of these complement events is again the double shaded region, which is exactly the same as the shaded region in the first picture. So basically, if you have a complement of the union, you can distribute this complement operation over the sets. However, then you need to change the sign to an intersection, from a union to an intersection. Now, the second law of De Morgan is also stating something similar. It says that the complement of the intersection of two events is equal to the union of the individual complement events. Again, if you check, we have the intersection E intersection F in this white region, and everything else as an outcome in the sample space forms the complement E intersection F. Now, in the second part of this equation, in the right-hand side, we observe the union operation, and E complement is everything else outside E, and F complement is everything else outside F. But this time we are taking the union. This means we are taking everything except the intersection part. So similarly, again, if you are talking about the complement of an intersection operation, you can distribute this complement operation over individual events. However, this time you need to change the sign from intersection to union. So these two laws are going to be very practical. They are going to give us a practical use in calculation of many probabilities, and we are going to practice this later. But at this point, we are going to finalize our video by solving this first question, question 1. Imagine we have purchased a digital radio, and we are going to measure the lifetime of this digital radio in years. And how can I define my sample space? Of course, as non-negative real numbers, right? I mean, no matter which time unit you use, either years or hours or weeks or days, it does not matter. The sample space of this experiment is going to contain all non-negative real numbers from 0 to infinity. Now we are going to define three events. A is the event that the lifetime of the radio is at least 4 years. So how can you define event A? As a ray starting from 4 and until the infinity. So all the real values which are greater than or equal to 4, they form the event A as a subset of the sample space. Because the radio, the lifetime of the radio is to be at least 4 years in event A. Event B is the event that the lifetime of the radio cannot exceed 7 years, which means it is going to, in this event, it is going to break down in 7 years. And then the event B is represented as the subset of the sample space, which contains the real values between 0 and 7. Finally, event C is the event that the lifetime of the radio is at least 5 and at most 10 years. So, in other words, the event C can be defined as the event of the radio to work for at least 5 years, but break down before 10 years. So we are going to define event C as an interval subset of the sample space between 5 and 10. So all real numbers contained between 5 and 10 will be in this event. So in this experiment, as you can see, we have an uncountable sample space. And the events that we are defining are uncountable as well. As a summary of this question, we can say that our sample space is non-negative real numbers, and we have A, B, and C events defined in the form of intervals. Now, the question is asking us a list of set operations, basically. So what is A intersection B events? And we are going to provide a verbal explanation to these events as well. So we are going to state them qualitatively. Now start from A intersection B. So A intersection B is the intersection part of the interval between 0 and 7 and the ray from 4 to infinity. And that is the interval between 4 and 7. So A intersection B is the event that the lifetime of the radio is between 4 and 7 years. B intersection C. So B intersection C contains real values between 5 and 7. So B intersection C is the event that the lifetime of the radio will be between 5 and 7 years. How about A intersection C? A is the ray starting from 4 until infinity, and C is an interval between 5 and 10. Now, if you are careful, you will realize that the event C is already contained by event A. So this means what? If you observe that event C occurs, this means A also occurs, right? Because any outcome in C is also an outcome that we observe in A. A intersection C gives us C because C is also a subset of event A. Therefore, A intersection C is the event that the lifetime of the radio to be between 5 and 10 years. Now, how about A intersection C intersection B? Okay, all the three-way intersection. Now, you know that we can make these set operations in any order. We can calculate A intersection C. A intersection C is already equal to C. And if you take the intersection of C and B after that, you will realize that the three-way intersection of these three events is the event that the lifetime of the radio to be 5 and 7 years. How about the union operations? What is A union B? Now remember, in the union operation, we need to provide all outcomes that are contained in either the first event or the second event or in both events. Now A is a ray starting from 4 until infinity, and B is an interval starting from 0 to 7. Therefore, the union of these two events are going to contain everything starting from 0 till infinity, which is going to give us the sample space. So A union B as an event is the whole sample space, which necessarily occurs, right? So when you perform an experiment, because the outcome is going to be something in the sample space is also an event because it is also a subset of itself. Sample space is also an event which always occurs. Now A union C. A is a ray starting from 4 until infinity, and C is a subset of A already. So A union C will be equal to A, the event that the lifetime of the radio to exceed 4 years. Now, this first phase of this question were rather easy. Now we are going to make things a little more complicated. So let's start from the complement of B union C. Now, in order to define the complement of B union C, first let us define B union C. Then we can define its complement. Now, B is an interval from 0 to 7, and C is an interval from 5 to 10. Their union is going to be an interval from 0 to 10, and the complement of B union C is going to be a ray starting from 10 exclusively until the infinity. Okay, anything in the sample space which is not a part of B union C will be in its complement, right? So the complement of B union C is equal to the event that the lifetime of the radio to exceed or to be more than 10 years. Now, A union B union C. What is A union B union C? Actually, we have already determined that A union B gives us the sample space. So if you add C into that union, still you will get the sample space because everything is already there. So A union B union C gives us the whole sample space. How about A complement intersection B? First, we need to determine A complement. Remember, A complement is everything else in the sample space other than the outcomes in A. And A complement contains real values which are less than 4 and greater than or equal to 0. So the interval starting from 0 until 4, and 4 is exclusive, is going to be what? Is A complement. And that A complement set is going to be a subset of B as well. Therefore, if you take the intersection of A complement and B, you are going to get A complement exactly, which is the event that the lifetime of the radio to be less than 4 years. Now, we are going to answer J. What is J? The question asks, what is B complement intersection C complement? Now, at this point, you may answer me like, first we determine the complement of B, then we determine the complement of C, then we take the intersection. However, because we have learned something much more easier, we are not going to do this in that fashion. Okay, it is also a possible answer, but we can use De Morgan law. According to the De Morgan laws, the intersection of the complements of two events is equal to the complement of the union of two events. And we have already answered this question in part G, as you can see. So this answer for part J is also equal to the event of the lifetime of the radio to exceed 10 years. Finally, in the last part, we are going to determine B union C complement. And event B is the radio to have a lifetime that is between 0 and 7 years. And C complement is what? Anything else outside this. Now, in C complement, the lifetime of the radio can be at most 5 years, or it should be at least 10 years, but not between these two values. And if you take the union of B and C complement, then we should represent this event as the lifetime of the radio to be between 0 or 7 years, or to exceed 10 years. So this union event can only be represented in the form of these union events.